All right, welcome back to the deep dive. Today we're tackling something pretty complex, but also really exciting. We're looking at how machine learning can be used to better understand the brain, specifically through something called knowledge graphs.
Yeah, knowledge graphs are a fascinating way to organize information. Basically, think of it like a map, but instead of physical locations, it's a map of concepts and how they relate to each other.
Right, so like in this case, a cognitive neuroscience knowledge graph, a CNKG, would show you all the different parts of the brain, the functions they perform, how they connect, even how diseases might affect them. It's a way to see the big picture of how our brains work.
And that's incredibly valuable for researchers, for clinicians, for anyone trying to make sense of the overwhelming amount of data we have about the brain.
But building these knowledge graphs, keeping them up to date, it's a massive undertaking, traditionally requiring a lot of, manual labor from experts, reading through tons of research papers, identifying key concepts, figuring out how they all fit together. It's a really time-consuming and, frankly, error-prone process.
Absolutely. And that's where this paper we're looking at today comes in. It's titled XKGLLM, Leveraging Large Language Models for Automated Expansion of Cognitive Neuroscience Knowledge Graphs.
So using AI, essentially, to help us build better brain maps automatically.
Precisely.
Okay, so let's get into the details. What's so special about this XKGLLM framework? What did the researchers find?
Well, first and foremost, XKGLLM utilizes large language models, or LLMs, which are incredibly good at processing and understanding huge amounts of text. The same kind of technology that powers things like chatbots and machine translation.
Right, so instead of having humans painstakingly read through mountains of research papers, the LLM can do a lot of that heavy lifting.
Exactly. And they've shown that this approach can lead to significant improvements in the quality and completeness of these CNKGs. For instance, they saw a substantial increase in what's called precision, which means how often the system correctly identifies a relationship between two concepts. That jumped by almost 7%, reaching a pretty impressive 0.80.
So out of every 10 relationships it identifies, 8 of them are accurate on average. That's pretty good.
It is, and even more impressive is the increase in recall, which is a measure of how many of the actual relationships that exist in the data the system is able to find. That went up by nearly 16% to 0.81.
Wow, that's a big jump. So it's not just becoming more accurate, it's also finding more of the important connections that are out there.
Exactly. And this is reflected in the overall F1 score, which gives us a balanced view of both precision and recall, which also saw a significant boost, nearly 12%, reaching 0.8805.
Okay, so the LLM seems to be doing a really good job of understanding and capturing the relationships within the text. But what about the overall size and structure of the knowledge graph itself? Did that change?
Absolutely. The number of those crucial connection points, of what we call edge nodes, increased considerably. They saw increases of over 21% in one measure and almost 32% in another.
So the graph is getting much bigger, more comprehensive. That makes sense if the LLM is finding all these new connections. But I also noticed they talked about graph density and diameter. Can you explain what those are and how they were affected?
Yeah, these metrics give us a slightly different perspective on the structure of the expanded knowledge graph. While the graph definitely grew in size, the density actually decreased a bit. It's kind of like, imagine you're building a social network.
Okay, I'm following.
You add a bunch of new people, but they don't all necessarily know each other. So the network gets bigger, but the connections between any two random people might become less direct.
I see. So in the knowledge graph, that might mean that as we add more information, the paths between more distantly related concepts could become longer, less direct.
Exactly. And that's also reflected in the diameter of the graph, which is essentially the longest of the shortest paths between any two concepts. That went from 13 to 15, indicating that on average, it might now take a couple more steps to find connections between certain pieces of information. Like, you might need to click through a few more links to get to the information you're looking for, even though there's more information overall.
Interesting. So a bit of a trade-off there. More knowledge, but perhaps slightly less direct connections. Now, what about the computational demands of all this? Running these large language models, building these huge knowledge graphs, it must take a lot of computing power.
Yeah, it's definitely something to consider. They looked at the time and space complexity of their system. Time complexity refers to how the time it takes to run the algorithm increases as the amount of data grows.
Right, like does it slow down significantly as the knowledge graph gets bigger and bigger?
Exactly, and they found that their system actually improved the time complexity, meaning it can handle larger amounts of data more efficiently than previous approaches. But the trade-off is that the space complexity, which is the amount of memory the system needs, actually increased.
So faster processing, but it takes up more memory. Okay, that makes sense. Now, but before we get into some of the more specific details of how XKGLLM works, I think it's helpful to step back and look at the bigger picture here. How did we even get to the point where we're using AI to build these knowledge graphs? What's the history behind this kind of work, especially in fields related to biomedicine and healthcare?
Well, the idea of using graphs to represent knowledge has been around for a while, but it really started to gain traction as the amount of data in various fields exploded. In biomedicine, early efforts focused on creating these knowledge graphs manually, which was a huge undertaking.
Yeah, I can imagine. So what were some of the key milestones, the breakthroughs that led to more automated approaches?
Well, we saw systems like Polaris X emerge, which focused on identifying new terms and concepts from text sources like news articles and social media. What's interesting about Polaris X is that it aimed to be language independent, using models like multilingual BERT to process text in different languages.
So already a move towards more automated and adaptable systems.
Definitely. And there were also efforts focused on tackling specific problems within biomedicine. For example, in drug discovery, researchers started using knowledge graphs to explore new uses for existing drugs.
Oh, like finding out that a drug developed for one disease might also be effective for treating a completely different condition.
Exactly. By combining data about genes, diseases, and the effects of various drugs, they could use knowledge graphs to uncover hidden connections and potentially repurpose existing medications. They even developed methods to predict new drug indications by analyzing the shortest paths between concepts in the graph, sometimes even taking into account where specific genes are active in the body to improve the accuracy of their predictions.
That's fascinating. So the initial focus was often on addressing specific, well-defined problems within biomedicine.
Precisely. And the importance of these knowledge graphs really became clear during events like the COVID-19 pandemic. We saw the rapid development of healthcare knowledge graphs that were used to gather and organize information about the virus, its transmission mechanisms, and potential treatment approaches.
Right, trying to make sense of a rapidly evolving situation.
Exactly. These graphs proved essential for supporting clinical decisions, and they also played a crucial role in combating misinformation, helping to identify and flag potentially inaccurate or misleading claims about the virus.
So a really critical tool in a time of crisis.
Absolutely. And the creation of large-scale biomedical knowledge graphs, like the PubMed knowledge graph, which integrates data from millions of research abstracts, further demonstrated the power and potential of this approach. But it was the emergence of large language models, LLMs, that really revolutionized the field of knowledge graph construction and expansion.
So how did LLMs change the game?
Well, LLMs have a much deeper understanding of language compared to earlier methods. They can capture nuances and context in a way that was previously very difficult. For instance, projects like DiamondKG highlighted how important context is when understanding drug indications.
What do you mean by context in that sense?
Well, they found that a large percentage of drug uses are actually specific to certain medical situations. It's not just about a drug treating a disease, it's about understanding when and how that drug should be used based on the specific circumstances of the patient. LLMs, with their sophisticated language processing capabilities, are much better at capturing these nuances.
That makes sense. So LLMs allow us to move beyond simpler rule-based systems and build knowledge graphs that are much more nuanced and context-aware.
Exactly. We saw the development of frameworks for treatment discovery that leveraged the vast knowledge contained within LLMs to build comprehensive knowledge graphs spanning the entire medical field. Models like RegulaGPT showcase the ability of LLMs to understand complex biological processes like molecular regulatory pathways, capturing the subtle details of how genes and proteins interact.
So it's not just about identifying entities and relationships. It's about understanding the underlying mechanisms and processes.
Precisely. And this led to more personalized approaches as well. Researchers began exploring the use of LLMs to create patient-specific knowledge graphs that could be used to aid in personalized medical decision-making and even diagnosis. We saw systems like RAM-eShar, which used LLMs to process electronic health records and extract valuable information from medical predictions, and Dr. KONOWS, a diagnostic reasoning system that combined knowledge graphs with medical terminology to improve the accuracy of diagnoses.
So we're moving from broad general knowledge graphs to much more tailored and personalized representations.
Exactly. And the ReLM model went even further, integrating clinical notes and time series data using a technique called retrieval augmented generation to boost diagnostic performance even more. It's worth noting that this isn't just limited to Western medicine either. There's been exciting progress in applying LLMs to build and enhance knowledge graphs for traditional Chinese medicine, demonstrating the broad applicability of this approach.
It's incredible how quickly this field is evolving. So that brings us back to XKGLLM, which specifically focuses on cognitive neuroscience. Can you walk us through the key methodological steps the researchers took in building and evaluating this system?
Sure. So they started by gathering a large and diverse collection of data, specifically scientific articles and clinical reports relevant to cognitive neuroscience, particularly those focusing on stroke and neurological disorders. This data was pulled from open access repositories like PubMed, ensuring a broad and representative sample of the current knowledge in the field.
So a solid foundation of information to work with. What did they do with all that text once they had it?
Well, the next step was to pre-process the text to prepare it for analysis by the LLM. This involved several steps, starting with tokenization, which is basically breaking down the text into individual words and sentences while trying to preserve the meaning and grammatical structure. For this, they use common tools like Spacy and NLTK.
Right, sort of like getting all the ingredients ready before you start cooking.
Exactly. Then came normalization, which involved things like converting all the text to lowercase, removing unnecessary punctuation, and applying stemming to reduce words to their root forms. All of this helps to standardize the text and make it easier for the LLM to analyze.
Makes sense. But given the highly specialized language used in scientific papers, I imagine that accurately identifying the key concepts, the entities, was particularly challenging. How did they handle that?
Yeah, that's a crucial step. They used a pre-trained named Entity Recognition, or NER, model that was specifically designed for biomedical and clinical text. This model was able to automatically identify and label important entities like specific diseases, relevant biomarkers, and different treatment methods.
So it could distinguish between, say, stroke as a disease and thrombolysis as a treatment for stroke.
Exactly. That's really important for accurately capturing the relationships between these concepts. And they didn't stop there. They also used dependency parsing to analyze the grammatical structure of the sentences and figure out the relationships between the identified entities.
So not just identifying the pieces, but figuring out how they fit together.
Right. For example, dependency parsing can help differentiate between a biomarker that is simply associated with a disease and a treatment that is actually used to treat that disease. These subtle linguistic cues are really important for building an accurate knowledge graph.
Okay, so after all that careful preparation, how did they actually represent the cognitive neuroscience knowledge graph itself?
They use a directed graph, which you can visualize as a network where the nodes are the entities, like brain regions, functions, diseases, and the edges are the relationships between them.
So a node for hippocampus connected to a node for memory with an edge labeled involved in.
Exactly. And to represent this mathematically, they used what's called an adjacency matrix, where each entry indicates whether or not there's a connection between two entities. But they went a step further and introduced a confidence-weighted matrix as well.
Oh, interesting. What's that for?
This matrix captures the LLM's confidence in the validity of each relationship. So instead of just saying that a relationship exists or doesn't exist, they also have a measure of how certain the LLM is about that connection based on the evidence it found in the text.
That makes sense. It's like saying, we're pretty sure these two things are related, but we're not 100% certain.
Right. And this confidence score is then used in the automatic expansion process. The LLM reads the text, identifies potential new entities and relationships, and assigns a confidence score to each one. If the confidence exceeds a certain threshold, the new relationship is added to the knowledge graph, along with its confidence level.
So it's constantly learning and updating the graph based on what it's reading and how confident it is in its assessments. That's pretty impressive. They also used this idea of confidence to do probabilistic link prediction, right?
Yeah, that's a really interesting part. They used a Bayesian framework to try to predict new connections that might not be explicitly stated in the text, but are strongly implied based on the existing structure of the graph and the LLM's confidence in related connections.
So it's like the system is making educated guesses about what other connections might exist based on what it already knows.
Exactly. It's trying to fill in the gaps and make the knowledge graph even more complete. Now, to evaluate how well all of this works, they took a very thorough approach. They used standard metrics like precision, recall, and F1 score to assess the accuracy of the relationships identified by the LLM, comparing them to a manually curated set of known relationships.
And those were the metrics that showed those really impressive improvements, right?
Exactly. But they also looked at the bigger picture, using metrics like vertex growth and edge growth to measure how much the knowledge graph actually expanded in terms of the number of entities and relationships added. They also looked at graph density, which, as we discussed, showed a slight decrease, indicating a more sprawling but potentially less directly connected structure.
Right, that trade-off between more knowledge and potentially less direct connections.
Yeah.
And they also did some checks for consistency, right, to make sure the new information wasn't contradicting what was already in the graph.
Absolutely. They looked for potential conflicts between the newly added relationships and the existing knowledge, and they did find a slight increase in the conflict rate. This suggests that while the LLM is very good at extracting information, it's not perfect, and some of its inferences might not always align perfectly with the existing knowledge base.
Makes sense. It's still a learning process. And they also looked at the computational efficiency, as we discussed earlier, finding that improvement in time complexity, but an increase in space complexity.
Exactly. They also evaluated their probabilistic link prediction capabilities, comparing XKGLLM's performance against several other well-established knowledge graph embedding models using standard link prediction metrics. While XKGLLM showed promising results on some data sets, it wasn't consistently superior across the board, suggesting that there's still room for improvement in this area.
Right. Always room for improvement, but still a significant step forward. And it's not just about the numbers, right? They also involved experts to actually look at the quality of the information being extracted.
Yeah, that's crucial for real-world applications. Domain experts in cognitive neuroscience reviewed the LLM's performance on tasks like named entity recognition and relation extraction, comparing it to existing, more manually curated knowledge graphs. The results were generally positive, often showing performance comparable to or even exceeding these existing resources.
That's really encouraging. It suggests that XKGLLM can potentially be a valuable tool for researchers and clinicians. And finally, they also analyzed the overall structure of the expanded knowledge graph using complex network analysis techniques.
Right. They use software like GIFI to calculate things like the average clustering coefficient and the diameter of the graph, comparing the XKGLLM expanded graph to both the original CNKG and several other well-known complex networks from different domains. This analysis provided further insights into the overall connectivity and organization of the cognitive neuroscience knowledge graph after it was expanded by the LLM.
So putting it all together, it seems like XKGLLM is a very promising approach for automating the expansion of these critical knowledge graphs in cognitive neuroscience. It's not perfect, but it offers significant improvements in accuracy and coverage while opening up exciting new avenues for research and applications.
Definitely. It highlights the immense potential of large language models for accelerating knowledge discovery and organization in complex scientific fields like cognitive neuroscience.
Okay, so now for our novel notions segment, where we take these findings and think about what they might mean for the future. What are some of the exciting, maybe even a little bit futuristic research directions that this paper inspires?
Well, one idea that really stands out is the possibility of integrating real-time neuroimaging data into this kind of framework. Instead of just learning from static text, what if the LLM could also learn from live brain activity data captured through technologies like fMRI or EEG?
So we'd be moving beyond just representing existing knowledge and actually incorporating real-time observations of how individual brains are functioning.
Exactly. Imagine a system that could dynamically update the cognitive neuroscience knowledge graph based on what's happening in a person's brain at that very moment.
That's incredible. How would that work in practice?
Well, you could train the LLM not only on text, but also on patterns of brain activity that are known to be associated with certain cognitive states or disease markers. As new neuroimaging data comes in, the system could analyze it in real time, identify the active brain regions and their connections, and then, using its knowledge of the existing graph, potentially map those activities to corresponding concepts and relationships, or even infer new connections that are specific to that individual's brain state.
So you'd essentially have a personalized knowledge graph that's constantly evolving as the person's brain activity changes.
Exactly. That opens up some really incredible possibilities. For example, imagine using this kind of system to guide neurofeedback or neuromodulation therapies. By observing how real-time brain activity relates to the knowledge encoded in the graph, clinicians could potentially tailor interventions much more precisely.
It's like seeing the effects of a therapy on the brain in real time at the level of individual concepts and relationships.
Precisely. This brings together the power of LLM-driven knowledge expansion with the exciting fields of personalized medicine and real-time brain monitoring. It could lead to a much deeper and more personalized understanding and treatment of neurological disorders.
That's a truly revolutionary vision. It takes the concept of a knowledge graph from a static database to a dynamic, living tool for understanding and potentially even interacting with the brain on an individual level.
It's definitely something to think about.
Well, that wraps up our deep dive for today. Thank you so much for joining us as we explore the fascinating world of XKGLLM and the potential of AI to transform our understanding of the brain. For those who want to dig deeper into the research, you'll find a link to the paper in the show notes.
As you ponder the possibilities of these automated knowledge systems and their implications for the future of research in clinical practice and cognitive neuroscience, consider this. As LLMs continue to advance in their ability to understand and synthesize complex scientific information, will these dynamic, ever-evolving knowledge graphs ultimately reshape the traditional roles of researchers and clinicians in the fundamental processes of scientific discovery and medical diagnosis? It's a profound question that's worth pondering as we navigate this exciting new era of AI-driven knowledge expansion.
Thanks for listening, and we'll see you next time on The Deep Dive.